Welcome to Grid Unlocked, Falmouth's Energy Future. I'm John Madsen. I'm a resident of West Falmouth, and after about 39 years, I'm a soon-to-be retired faculty member from the Department of Earth Sciences at the University of Delaware. So I'm glad to be here today, and I'll be acting as the moderator for today's meeting. We're here for a fact-based community conversation on how the electric grid works and what's next for Cape Cod. Luckily, we have with us a panel of experts from Eversource that will explore the grid's current challenges, innovations, and the path forward. We provided note cards for you to write down any questions that you might have, and we plan to leave plenty of time for a question and answer session after our experts' presentations. And we have a special guest with us today, and let's see how technology works here. Miles, can you hear me?
I can, John. How are you?
I'm great, and the audience can hear Miles as well. Miles O'Brien.
Hear me out there?
Everyone's here. Miles O'Brien is a distinguished independent journalist who focuses on science, technology, and aerospace. He serves as the science correspondent for the PBS NewsHour and is a producer, director, writer, and correspondent for the acclaimed PBS documentary programs Nova and Frontline. And to the great benefit for our community, Miles has recently become a resident of West Falmouth. So Miles, you're clearly not here with us at the Falmouth Public Library. Can you tell us where you are and what you're doing there?
I am steaming across the Southern Ocean, having just left Antarctica, and I came to Antarctica to avoid the cold temperatures and snow in Falmouth. I am a snowbird who didn't know when to stop, I guess. And in honesty, you've had it worse than I have. I've been on this Korean icebreaker for 55 days or so. Who's counting? And we have been at the Thwaites Glacier, which is widely known as the so-called Doomsday Glacier. It's a very unstable glacier that holds inside of it about 2.5 feet of sea level all over the world should it melt, and it is melting very quickly. And I'm on a vessel filled with scientists who've done numbers of studies to try to characterize it, understand it, and really get a handle on what is happening, why it is melting so quickly, in many cases, tens of times quicker than its neighbors. And it's been a fascinating way to see how scientists attack and try to characterize a difficult problem, John.
Great. Miles, we're here to hear from Eversource energy experts on how the electricity grid operates and inform us on what's being done to ensure a reliable energy future for Cape Cod. So what are the connections, do you think, between the scientific research that you're reporting on from Antarctica and what we will learn about here tonight in Falmouth? In other words, how does the operation of our regional electricity grid link to global climate issues?
Well, for me, John, this is kind of closed a cause and effect loop. The reason these glaciers are melting is because we're burning fossil fuels like crazy. There's no scientific debate over that. So fossil fuel burning cause, effect is glacier melt at unprecedented speed. And can we adapt to that is the other part of that whole circle. We have to think about, first of all, building a grid that doesn't contribute to the problem. And there are lots of ways to do that. And fortunately, renewables now are in the category, and I'm sure the Eversource people will confirm this, are the cheapest option in many cases, and certainly fastest to the grid. And we're not reliant upon the swings of cost of natural gas and so forth. So there's that whole component of resilience and economic resilience. And then, of course, those of us who live in Falmouth and who are fortunate to be there, we know exactly where the sea level is. It's right outside our doorstep. And it's important. While the Thwaites Glacier isn't going to melt tomorrow, but it could melt in the next few decades if we don't stop what we're doing. So this goes right to the heart of how we keep the lights on. We have to think about doing it in a way that isn't going to exacerbate that problem. And we also have to think about doing it in a way that is resilient as we deal with the effects of what is kind of baked in already.
Thanks, Miles. We truly appreciate you joining us on your way back from Antarctica headed towards New Zealand. The weather looks comparable to what we have here, so hang in there. I can think of no better example that you gave us today than thinking globally and acting locally. And thanks for the perspective that you've provided. You're welcome to stay on the Zoom. It might get a little chilly for you as we go through, but it was great talking to you, and we hope to see you back here in West Falmouth soon.
Won't be long, and I'm sorry I'm not there, but I look forward to hearing about the conversation.
Great, thanks, Miles. Switch gears here a little bit, get to PowerPoint slides. Oops, slideshow. So next I'd like to introduce Ronit Goldstein, Community Relations Manager from Eversource. Ronit will sort of set the stage for us and introduce the speakers from Eversource.
Sure.
Turn over to you.
You want me to stand in front of the mic?
Yeah, that'd be great. Forward, backward, and that's a pointer.
That's forward, backward?
Yeah.
Okay. Sure. Good afternoon, everyone. I've never been told that I can't be heard, but I'm just doing a sound check here to make sure that you can hear me. Great. I'm Miles, if you're still on, I am thoroughly impressed with, I mean, we have people that came from not quite as far as where you are. So I'm thoroughly impressed, and the technology made him sound like he was right in the room with us here. So, John, thank you for the introduction. I don't know where you went. Sorry, you're right in front of me. For those whom I've not yet met, I'm Ronit Goldstein. I'm the manager of community relations. I've had the privilege of working for Eversource for almost 8 years now. And before I introduce my colleagues whom I'm accompanying today and supporting, I just wanted to kind of connect the last forum that we had in December 2024. We met here in this room. I think it was hosted by the Energy Committee. Stephanie, you could keep me honest, but I believe back then it was as well a joint effort that Eversource was invited. And we focused on the electric sector modernization plan, which is more on the distribution side of the house, if you want to call it. And today we've been asked to come in and talk a little bit more about the role the transmission plays. So it's not okay. It's not moving. So should I try the keyboard?
Yeah.
No? Oh, there it is. Keyboard works. We'll use old school here. We hope that you enjoy what we have to share with you today. We'd love to do these types of forums and have an open dialogue. We do ask so that we have enough time to have questions answered. Sort of housekeeping, we thought that it made sense. Hopefully everybody has an index card, or if they have a question that they want to jot down, and hand that index card or piece of paper to either myself or Stephen Dudek or Lisa, who is waving in the back of the room, and we can collect those questions and allocate time at the end to answer your questions. So I'm accompanied, I'll sort of go down the slide. I've got with me Jacob Lucas. If you want to just, Eversource folks, give a wave. The Vice President of Transmission System Planning. Johnny Dong, who is the Director of Transmission System Planning. Thanks, Johnny. Carissa Sedlak, who is the Director of Transmission Interconnections and Solutions. And Juan Martinez, who is the Director of Distribution System Planning. And our presentations are really, were formed from some of your questions and interests and concerns. And so we will be talking about giving an overview of how the ISO New England grid operates, current and future energy mix trends, and the region's 5 to 10-year grid outlook. Evolving clean technology resources will shape future grid performance and energy prices, talk a little bit about that, and then planned transmission upgrades and clean energy integration, wind, solar, nuclear, including reliability costs and local impacts such as the Cape Cod Country Club solar project. There were folks that took an interest in how that plays into it and what Eversource is doing to support that project. So I think I talked about housekeeping already, and so with that, I'm going to manage this presentation and pass it over to Jacob. Do you want to do your slides on your own?
Sure. Yeah.
Okay, great.
Thanks, Ronit.
Just stand by.
Yep. Okay. Good afternoon, everyone. Happy to be here. What a great turnout. I'm going to give a quick overview of myself, kind of my origin story. I'll talk a little bit about Eversource, but then I'll dive into the questions. These are some really good questions, so thanks for sending them along. Really helped us kind of frame our presentation. So my name is Jacob Lucas. I'm the Vice President of Transmission System Planning at Eversource. I've been in the power industry for about 25 years. I wish the kind of the beginning of it was more romantic than this. It was just Duke Energy was the only one that called me back when I needed an internship. That's how I landed in it. But that was down in North Carolina. I fell in love with it. So I just wanted to say this is a personal and professional passion of mine. I'm an electrical engineer by education with a master's degree from WPI. And so I've been doing this about 25 years, all on the technical side, design side, planning side. With a brief hiatus, I went down to DC and I worked at the Federal Energy Regulator in Washington, DC for about 7 years. So I do have that federal kind of policy background as well. So these are the questions that we received. I'm going to start off with the one that's asking about how does the ISO New England electric grid operate. Before I do that, though, why am I even qualified to kind of answer this question? So what transmission system planning is my team's essentially responsible for the longer term computer simulations and studies that essentially identify what system needs and system modifications are needed 10 plus years out in the future so this grid remains reliable. That's what my team does. I also, through a joint venture that we had with Ørsted, a Danish company, the largest offshore wind developer in the world, Eversource had a joint venture with Ørsted where I was also on the front lines of building the South Fork, Sunrise, and Revolution offshore wind farms. So I have that experience. But just real quick overview about Eversource. So Eversource is New England's largest utility with 4.5 million customers, mostly in the states of Connecticut, New Hampshire, and Massachusetts, including powering this building where we are here today. And we also control, it gets a little complicated in Massachusetts because National Grid there's some holes where National Grid is the service provider, but Eversource also does supply Boston, which we will be talking about a little bit later. So, okay, let's just dive in. I'm gonna use the keyboard. Okay, so the electric grid is often described as the largest, most complex machine ever created by humankind. I'm going to try to summarize it in about 2 minutes. So wish me luck. But it is important to kind of set up that kind of foundation here first. So at the highest level, the high voltage transmission lines, which in New England are generally 100,000 volts and higher. So these are the really large structures that you see in open right-of-ways, not the lines on community streets. Those are distribution lines. What the transmission system does is it essentially connects the large-scale power generators with load zones, let's call it, because it's then from those zones where the lower voltage electric distribution lines then take it from those substations to your actual homes. That's the quickest explanation I can give here. We're going to jump into some more details here about New England in particular, because one of the really complicated aspects of the electric system is balancing load and generation. Now, this is where system frequency kind of comes from, because anytime there's an imbalance between generation and load, system frequency can get thrown off. It's the number one thing that operators look at in the control room. If you ever go to the control room, they have a giant board that's telling them real time what the system frequency is. But as planners, these are the two factors that we often think about most: what's happening with electric load and what's happening with electric generation. So in the upper left here, these are data from 2025. I'm not going to have time to go into all of this, so I'll just try to touch on the highlights, and I'll circle back to the question, because the question was kind of asking about how does the system operate and how do we exchange power with our neighbors. And so that's why I included the map on the right, which I'll touch on, and then the bottom left is a typical summer day resource mix. So starting up in the upper left, going into every summer, ISO New England does a independent system operator of New England, who mostly controls the energy markets in New England, does a summer outlook to see how things are looking going into the summer. These are the numbers from 2025. I did include the actual peak there in the red box, but just real quick, ISO New England was expecting loads to be around 24,800 megawatts on a typical weather day, up to as high as potentially 26,000 megawatts on an above average weather day. And an actual 2025 peak during this summer on June 24th was 26,135 megawatts. So loads were pretty high this summer. There's roughly approximately 30,000 megawatts of available electric generation. What I really want to call your attention to here is New England's all-time record peak happened in 2006. and that number is the bottom number you see there, 28,130 megawatts. And so one kind of takeaway here is it's pretty fascinating. 20 years later, roughly, we are still working our way back up to where our all-time record peak was, which was around 28 gigawatts. So that's kind of the one thing I wanted to draw your attention there. This just happened this summer. But importantly, on the map on the right, so what is the map on the right showing you? So the circles that are sized by capacity output, generator output, those are the large-scale generators in New England. There's too many fuel types that I don't have time to go through, but yellow is natural gas, because that is the highest concentration of capacity that we have in New England. So if you wanted to ever see them all laid out on one map, there it is. But also, I have aggregated there are 14 transmission lines that interconnect New England to its neighbors, 14 in total. And I've grouped them by neighboring region and included the normal direction of flow and the total transfer capability essentially between us and that region. So I'm not going to go through them all again, but I gave these numbers to confirm to your reference later. But New Brunswick, for example, we're normally importing from New Brunswick, New England is, and it can go up to as high as 2,500 megawatts. Hydro-Quebec, I just recently had to increase this number because the New England Clean Energy Connect project was brought online a few weeks ago. We can import approximately 3,200 megawatts from Hydro-Quebec. New York, this is several transmission lines along the western border. Again, remember, I'm aggregating them here, but really we exchange power very frequently, and it goes back and forth in both directions to New York. That can be approximately 4,500 megawatts. And then Long Island, we are normally exporting on the Crosstown cable, which is going to Long Island, and that could be about 500 megawatts. Now, what's important about these ties and to understand how the system actually operates, some of these are controllable and some are not. And what that means is, you might have heard of high voltage direct current lines. They're called HVDC lines. HVDC lines are generally more controllable than a normal high voltage alternating current or HVAC transmission line. And so in terms of how the flows actually happen on a real-time basis, it's largely driven by physics. And this is something I'm going to touch on again later, but the major load pockets. I gave you the overall New England wide numbers over here. The major load pockets in New England, as everyone could probably guess, Boston and Southwest Connecticut. So generally, on a typical day, there's not a lot of generation internal to the Boston load pocket. And so therefore, you'll normally see flows like into Boston and then southwest into Southwest Connecticut. That's generally how the powers are flowing on an average day. For example, you can see the large concentration of yellow circles there in the Rhode Island, north of Rhode Island there. Those generators are often flowing into Boston because Boston's the largest load pocket. And then real quick, I did want to touch on the typical summer day resource mix. No surprises, the largest percentage here is natural gas at 37%. I did want to call out the imports, though, shown in purple, 23%. So New England is a net importer right now of power on any given summer day. I did want to give an example, though, about how these flows are evolving. And this is a fairly recently new phenomenon. And I'm going to use Falmouth as an example, or Cape Cod as the example to kind of illustrate this. Because for the longest time, right, so the blue lines, so these are all the transmission lines in New England. Blue are the highest voltage that we have, 345,000 volts. And so the higher the voltage, the more efficiently it can deliver power. There are less losses. And so the blue lines in the map, the blown out map you see to the right there, are all kind of leading down to the canal generators there right on the Cape Cod Canal, but then onto the Cape as well. And historically, a lot of these flows have been to supply Cape Cod. And this is getting completely reversed now with the addition of the Vineyard Wind offshore wind farm. Because even especially in the winter, right, the capacity factors for Vineyard Wind will likely be higher in the winter, especially in the winter, and loads on Cape often cited in the decarbonization roadmap. And really, I just wanted to kind of draw your attention to kind of one important thing. Obviously, if you saw that I said today we currently have about 30 30,000 megawatts of total generation. That was on the first slide under the summer outlook, about 30,000 megawatts of total generation. You know, in this scenario of the 2050 future, there is 90,000 megawatts of just offshore wind and solar. So just offshore wind and solar to make this scenario work will require about triple the amount of the total generation that we have today in New England. So it's a staggering amount, but Eversource is working, which my colleagues later will talk about. We are working very diligently to try to help facilitate the interconnection process of bringing on as much solar as possible. And that is where we're going to talk about the current and future status of the grid. So this is where we're going to transition from transmission to distribution, which is why Juan Martinez is going to kind of help me with this part. But I did want to, so this is from ISO New England's capacity and energy load forecast. But I thought it did a nice job, and every year ISO New England updates this. I thought this is talking about energy now. So in planning, we normally are trying to make the peak power. We're planning for the peak instantaneous amount of power that the region can use, but this is just talking about energy. And so it's just kind of interesting again that from 2005, 2006, when New England kind of peaked, it's been steadily declining since then. ISO New England is forecasting a pretty large increase in both energy usage and peak, electric peak, which you'll see on the next slide, largely driven by electric vehicles and space heating. And the number, just so you know, over the next 10 years, ISO New England is expecting energy usage to increase by roughly 11%. Now here, this is the net peak forecast. So this is like the instantaneous peak number. This is again what we plan to. Today, like I said, they had forecasted 24.8 gigawatts for this summer. It actually came in above that at 26,000 megawatts. And so what's interesting here is this is showing the next 10 years and what ISO New England is forecasting for system peak. This is a 50-50 forecast. We plan for both a 50-50, which is essentially the lower of the forecasted numbers. And then we also plan for a 90-10. That's kind of your above average temperature day. You can see now all the way out into 2034, ISO New England is forecasting a 26,897 megawatt for the entire region. You know, it's kind of an interesting number when you remember that even this summer we hit 26,100. So we'll see how this gets adjusted every single year, and we'll see over the next few years if that, you know, where that number tracks. And so I'm now going to turn it over to my colleague Juan Martinez to talk about the distribution load forecast that we do at Eversource.
Good afternoon, and first of all, thank you for inviting me. I didn't have the time to say that, but as you can see, we're very passionate about this. So anytime, any opportunity we have to come and share the information, you know, I really enjoy that. So thank you for inviting me. As Jacob mentioned, well, I've also been in the utility industry for over 21 years, but on the distribution side. So, you know, I'm going to cover that distribution part of the presentation, okay? What am I showing here? I am showing basically now, if you remember that slide that Jacob showed, is the transmission down to the substations. And we call these distribution box substations. They basically have, you know, no moving parts, no emission. These are just where we transfer that voltage from the transmission level voltage to the distribution level voltage. So what I'm showing here is what forecast we have, because as distribution planners, we do the exact same thing at the substation level. So we see how much load we see every year in these substations, and then we account for all the new business and all the growth, and we say, okay, what do we see in the next 10 years, right? And this is what that chart shows. So we took all the substations in this area, and we added up their peak demands, and we basically plotted for the next 10 years. And just to give you an idea of magnitude, because we talk megawatts and megawatt hours, so, you know, a megawatt. Take your car and let's say drive along the street. And when you see the overhead transformers, right? You see the little transformers that are on poles? Drive around, and when you count 20 of them, that's how much area we can supply with just 1 megawatt, okay? So that's the magnitude that you can see. Just drive around, and when you count 20, that's only 1 megawatt. We're talking now hundreds of megawatts for the entire area, right? So that's the demand. Obviously, you know, in some areas it's higher, but just to give you an idea, it's a big area and just 1 megawatt So we're talking a lot of consumption here, a lot of demand of power. So what is the slide showing? We're expecting a significant increase in the next 10 years of demand. Some of that is, your regular, commercial growth or new business growth, but a lot of it also is electrification, right? So your electric vehicle growth, and sometime in the future, starting, after 2035. This is only summer right now, so this is only showing mostly summer peaking. So you air conditioning. This is what is affecting this. In the future after this, we'll also expect electrification to start playing a bigger role, even bigger than summer. But right now, this is showing the growth from 2025 to 2034 of your summer peak load for all the substations in the area, okay? And at the end of the day, you can see the growth in load. Next. Now we're asked, okay, so how do we do this, right? It is actually a yearly process. So every year, we actually measure all the loads in all the substations. And then we take that load, we compare it with the temperature that was that day. And then every year we do a forecast. We account for the things that we see in the future. It's a process that we do every year. During the summer, measure everything. Then between summer and, let's say, December, account for everything we know, everybody that applies, all the growth that we know, all the electric vehicle growth, and then develop what we call a forecast. And then we say, okay, now I have a forecast. Now I have to compare that with my system now. So what is the capacity of this station versus the load that I'm seeing? And then that's how we plan. Every year we do that cycle. That's what we're showing on the right side, is that wheel that we do every year. And then we develop plans. If we see violations, based on capacity or any other violations, we plan for it. We develop a plan, and we'll cover those plans later as we see them. But that's the yearly cycle that every planner goes through, almost, through the year. And why am I highlighting substations a lot and transmission line? As you can see, we're talking transmission line substations. Those are your key items when you have to upgrade the system, right? So there's three things that we do. We either upgrade the system because demand is growing, and I show you demand is growing. We replace equipments when they're defective or when they're obsolete, or we modernize the grid, right? Because technology. This part covers those large upgrades when we need new infrastructure, and the challenge is, you can see, it takes time, right? So we actually need to know. I hope it's not mine. So the challenge is we have to predict the future 10 years ahead, because if we need a new substation, we have to plan it today for 10 years ahead. So we can't be wrong in this. So that's why the yearly cycle, that's why the planning. And you can see the timelines, transmission 10+ years. Some of these timelines are very, they could be a lot longer than that. So this is basically a conservative number. A substation could be 5+ years. And then when you go down to the distribution, what you see on the street, that's a lot less time. So we show the forecast. I show you how we plan for it. After we run the calculations, and we did this year actually, this is what we need in the next 5 to 10 years for the system in the area. So this is what we have planned. So on the right side, I'm showing more of the larger scopes that we have, and then on the left side is the details. But basically, after we ran all the analysis for capacity, what needs to be upgraded, the key items that we have is, the Martha's Vineyard cable that we need to supply Martha's Vineyard, the Falmouth tab, which we'll cover more in detail later, but that's an upgrade that we need to do both at the transmission and distribution system. And then we have a new Dennis Brewster station that we need in that area for capacity and reliability as well. I'm also highlighting the CAPE SIP group. This is more related to DER, Distributed Energy Resources. So that was part of the SIP, which is where we group all the DERs and study them together. It's a lot more efficient that way. And as part of that, we received the PU approval to basically interconnect a large amounts of DERs as a group study, and the costs also get allocated as a group, and that's the CAPE group, the CAPE SIP group. We also do, as I mentioned before, we also upgrade equipment that's either, for asset condition purposes. So some of that work include replacing some switches that are, they are obsolete, basically, and replacing equipment such as capacitors. Those are basically, we use them to control the voltages in the system, but we have some obsolete versions that we need to upgrade with new ones. So that's what we call asset condition. And then we have upgrades now at the transmission level. And we'll cover some of this in more detail later, but this is also showing the transmission level upgrades that we need, such as the new 144 line between Bourne and West Barnstable. And then expansion of the offshore, and then K-Cap solutions, which we'll cover in detail later. And I'll pass it now to my counterpart, Johnny. So,
good afternoon. It's Jenny Do from Eversource. Nice meeting everyone. And I'm electrical engineer by training. I have been doing transmission planning for 17 years. So you can see all we're here are passionate engineers. So next few slides, I'm gonna go over some of the drivers for transmission infrastructure, why we need transmission, and then I'll zoom in onto the projects specifically in the Falmouth area. So transmission planning, we follow several procedures, and there are different drivers for transmission upgrades. The top one is that there are different level of reliability standards that we need to be compliant with. That includes the NERC, which stands for North America Electric Reliability Corporation. They set the original national standards for transmission system reliability. NPCC stands for Northeast Power Coordinating Council. They set up the transmission reliability standards for the Northeast region, including New England area, New York, Ontario, and Hydro-Quebec, so Northeast region. ISO New England is the independent system operator of New England. They also have a set of transmission planning standards for the New England area. Then as a transmission owner at Eversource, we have our own transmission planning standards. So we perform our studies and future planning, longer term planning of our transmission system that Jacob touched upon earlier, in accordance with this all this different level of reliability standards to make sure the system is reliable and safe to deliver the power at all time in normal condition, which is blue sky day, no outage on the system, and also we test force outage situations. If some event happens, it would take out a critical transmission line or other components on the system. We run those situations and those simulations to make sure the system can handle a certain level of outages as well without interruption to electricity supply. Then we also plan the transmission system. The second bullet touches upon some of the interregional transmission. Again, to tie to the map Jacob showed earlier, right? In New England, we're importing from neighbor regions, from New York, New Brunswick, Quebec. Then we, especially going forward, if there is no enough generation within the region, we really need to rely on the interregional transmission to make sure there's always balanced generation and demand at any real time. So we plan the system, and not only just looking inside of New England, we also model the different transfer levels. Oftentimes, the transfers are limited by the transmission system. There's a limited capacity, limited. It's not only the thermal, like how much power it can carry. There's also stability tests that we need to run on those interfaces. Then Juan touched upon the other big driver is the aging existing energy infrastructure. So due to asset condition issues, we keep monitoring the health of assets. We don't only replace some equipment only because of age. There's usually the issue either poor condition or, for example, transformer leak or underground cable, the insulation leak. There's environmental issue or safety issue, obsolete equipment, no repair parts, and we constantly have the asset condition program going on to address those asset health issues. Then, as we talked about earlier, in this Cape and the Southeast Massachusetts region, there are interconnection of offshore wind. The vineyard wind is already in service, and to interconnect large scale, that vineyard wind, the total capacity is 800 megawatts. To interconnect that scale of project, there are needed transmission upgrades, right? The cable to connect to
Recording in progress.
So the cable to connect to the wind turbines, right? Then the substation to accept the power and connect to the transmission network. That kind of upgrades are driven by the large scale wind project. There could also be upgrades driven by the distributed energy resources, like those smaller scale in the distribution system, solar, and even battery storage. So that's another category of driver. Then I'm gonna go to the next slide about the specific projects which would involve the transmission upgrades to support distribution load growth. So to the extent additional capacity is needed to support distribution load growth, oftentimes a new substation is needed. In that case, right, distribution planning identifies the capacity needed and roughly the area of the station. Then transmission planning steps in to figure out from transmission system-wise how to connect that station into the network. Eventually, right, the power has to flow to transmission, then go to the substation, then eventually go into the distribution load. So in addition to the interconnection of renewable resources and generation, there could be other interconnection-driven upgrades. Then any merchant entities, they can propose interconnection to the Eversource transmission grid. Then we provide kind of service to figure out what needs to be done in the system to accommodate the proposed resources or upgrades. So this slide has a list of projects going on, really zooming to the Falmouth area. And they're tied to the drivers I mentioned in the previous slide. For example, I'm not going through by the numbers. I'll just call out the category. To support the distribution load growth, number 7 and 8, the Falmouth tap upgrades are needed to support the load growth in this area. Then a new station is proposed To replace the existing Falmouth tap station. So, and it's combined with reliability planning because the existing station and existing system configuration shows reliability criteria violation. So by doing the 7 and 8, the Falmouth tap station together with a future line going into the station, we not only provide enough capacity from transmission and distribution to supply the load growth, we also meet the latest and greatest reliability standards of the planning. Then number one is folks here might be aware that's driven by capacity as well. It is a distribution project, but T&D planning oftentimes share similar principles. So Master Vineyard project, I believe, is almost going to be in service soon. It's under construction. Then the 2 and 3 about the ground fault over voltage prevention, that's driven by protection standards due to the DER interconnection. So 2 and 3 are driven by the system protection safety reasons. We need to upgrade the existing protection at these stations to prevent the DERs, distributed energy resources in the distribution system, like those solar, feeding a fault in the transmission system. That could be a safety concern as well. Then the 4 and 6, I'm calling out the category, are driven by the asset condition, the circuit switcher replacements, the existing switches, they have asset condition issues or reliability issues. They have misoperations, then that would pose reliability and safety concerns to the transmission system. Then number 5, the Hatchville station work of the mobile transformer. That's related to the Falmouth tap project. We kind of give a thorough list here. Although that's an interim project, is to ensure during the construction of the Falmouth tap project, the system maintains its required reliability level. With that, I'm gonna turn to my colleague, Carissa.
Thank you, Jane. Appreciate it. Hello, everyone. So nice to see such a full complement of people tonight. Appreciate it. Hey, I'm Carissa Sedlak. I am the Director of Interconnections and Solutions for the Transmission System for Eversource. So I see you guys had some questions about the interconnections, not necessarily the lines, whether it's transmission or distribution, but actually generator interconnections, which is what I do all day. By trade, like my colleagues, I'm an electrical engineer. I graduated from Syracuse University many, many moons ago. I've been in this industry for over 35 years. I started my career at an amazing hydroelectric facility in Niagara Falls, New York. It's 2,500 megawatts. Super cool place to get started, especially right out of college. I did work for ISO New England for over 23 years, and I've been here at Eversource now for 4. So it's my pleasure today to explain to you how the interconnection process works. Now, like Ronit, I might not know the right button. Perfect. I got that. So, you live in the Cape. You've probably been paying attention to the news, the signs on the lawns. You have a lot of offshore wind wanting to be developed. We have the Vineyard Wind Project, which has been generating excellent resource, especially with the high winds that we've been receiving. But we've been building out the transmission system, and as Juan pointed out, the distribution system as well, to accept more and more renewable technology, whether it's solar wind or even some battery storage if it's so chosen to be developed in this area. But why the Cape? Why the Falmouth area? It's your proximity to the Bohm lease area. So right now, the transmission that we've built out to date, which I'll cover in a moment, we can integrate upwards of 2,000 megawatts of offshore wind, which is just simply amazing given the fact that that required a build out of the transmission system near or around our current facilities here in the Cape. So we call it the Cape Cod Solution Program. And it was a co-optimized solution. So you heard Janie talk about reliability needs, NERC, NPCC standards. These are needs that we must address. It's not a choice. We must do what we need to do to maintain reliability so that your electrical vehicle can charge, your cell phone can charge, your TV can stay on, even if the Patriots lose. You get to see it all, okay? But that's because we have a robust transmission and distribution system that adheres to these reliability standards. But what happened with one of our offshore wind projects, when we were doing the studies, we realized there was a benefit to everybody by co-optimizing the transmission build out with the offshore wind. And that's how we developed the Cape Cod Solution Program. So this actually was really great. It's a couple of years old now, but folks like you actually benefit from the reliability benefits of building out the grids. Again, like Jacob pointed out, with all of this offshore wind, you are not bringing power into the Cape anymore. You're exporting it out to those load pockets. Your area is stronger than ever before, more resilient, especially as we see snowstorms come in. So you might ask yourself, what is the Cape Cod Solution Program? Like I said, it was multiple phases. Our first phase is actually already in service. Phase 1 went in service back in May of 2024, and this was the first step to enable more offshore wind or renewables in the area. Our second phase is in progress. As noted here on the slide, we have our permitting and siting in place. We're just working with the offshore wind developer to move things forward. Takes a little time, right? Takes a little time. You can't do anything overnight. So it will be a matter of years before everything is built out for phase 2. But I wanted to let you know today, this is in the works, and we're very proud of the work we're doing out here at the Cape to make sure we have a resilient grid for you guys. I threw this in here because I thought it would be great, just so you could see, you know, you're driving around the streets. What did Juan say? Start counting the little transformers on top of the distribution poles. Well, if you don't want to count transformers, then you know what? Go take a ride by one of our substations. You hear the crackle. It's kind of really exciting. I spent my early career listening to the crackle of a 345 substation on a cold day, and I'll tell you, it still gives me goosebumps. But these are the two places that we're building out the transmission system and the new substations. So the next part of my presentation today is really talking about how do these clean energy resources interconnect. I've been at a couple of town meetings here out at the Cape. I think it's very interesting that folks think that Eversource gets to pick. Guess what? We don't. So as I'll point out in these next few slides, ISO New England, they do the studies. We, Eversource, or the TO, supports the studies. We give you a cost estimate of what it's going to be to interconnect that renewable resource. So it's a robust process. It's governed by FERC. And in 2025, we actually decided to spice things up. And there is a new interconnection process under FERC Order 2023. So again, think about time I just said a few minutes ago. Came out, they wanted to do something in 2023. We actually didn't get the rules approved until 2025. So we're just starting to get through the study process, and that took 2 years alone. So think about how long it's going to take to build out that transmission. But anyways, there's a new process, and we're going to try to make things more efficient as we interconnect resources, all types of resources. But what we're seeing is primarily renewable resources in our interconnection grid. And by studying them in clusters, hopefully we'll be able to identify reliability needs that come out of those studies and do more co-optimization to reduce the costs for folks like you. So again, I emphasize, we Eversource do not get to pick where these renewable resources are going to interconnect. It's the developer that picks, and you might be asking yourself, well, why the Cape? Because the Bohm lease area is very close to Cape Cod and the islands, and therefore it's very efficient and less costly to bring that energy onto the Cape, build out the transmission system, make it more robust for folks like you, and then be able to deliver that energy to our load pockets. So this slide 29, just simply goes over the process, and you can see our role as the transmission owner and the role of the developer to pick the spot and go through the study process with ISO New England. So I heard there was a question about what incents renewable development. You know, what's the cost behind all that? It's very interesting. It's not one thing. It's maybe an RFP that a state is doing. Federal government, I'm sure nobody in this room is living under a rock and paying attention to the constant churn at the federal level about renewables. So we take all that in along with market conditions. If you think about what Jacob talked about in his first couple of slides, we are starting to be winter peaking, right? We're electrifying everything, whether it's your cell phone, electric buses in Boston or in Hartford. All of this is adding up that we're going to need a stronger grid, whether it's distribution or transmission, but we're going to need the stronger grid to also interconnect renewable technologies. So renewable developers are actually paying very close attention to the RFPs, tax incentives, market conditions, because it's, again, the property of supply and demand. If there's not enough supply, prices are going to go up, and those developers can make money. However, when a renewable developer wants to interconnect, as I noted on the previous slide, they do need to submit an interconnection request to ISO New England. It gets studied, and right now what we're seeing is quite a bit of battery storage, surprisingly, in the interconnection queue. But we still know that those wind projects are out there. They're just watching how the state incentives or the federal incentives are changing. But I do expect with the Bohm lease area so close here into the Cape Cod area, that you're going to see offshore wind come back and be something that's going to continue to be developed. There's actually quite a few projects that I speak to that are moving these projects forward. So next, I want to talk about distribution, because Juan, do you want to come back up and talk about? Oh wait, not yet. I'm sorry. Oh, sorry, I screwed up. Sorry, guys. One more. Thank you. Let me go through one more slide, and I'll turn it over to Juan, because I do want to talk about the distribution that's happening out at the Cape. But there was a question here about how much it costs to integrate offshore wind or solar. And again, it goes back to those tax incentives and what's happening at the federal or the state level. So location is the number one driver. Can I find a place that is close to the transmission grid or a distribution facility that makes it economic to build out that particular type of renewable? The longer the line is between the generator to the substation, generally speaking, it's going to be a more expensive generator, which means you're going to pay for that more expensive generator with your monthly electric bills. I also want to point out that every generator is a little bit different because of the hosting capacity of the grid. I think you heard early on that we're building out. When you build out the transmission system or distribution system, it isn't perfect. there's often extra hosting capacity. So it's very likely with the transmission and distribution build out that we're expecting, we're going to start to see additional hosting capacity open up, so the next offshore wind developer or the next solar project that comes to the table will be a little bit cheaper. Okay, and with that, Juan, it's over to you. And I will point out that I'm missing a thing. Okay.
Yes, and there was also a question about distribution costs, right? The cost for distributed generations and at the distribution level. So, we're including a link to where some of the costs are highlighted, like high-level costs of different items. But in general, for large DER customers that want to interconnect at the distribution level, right? What typically happened in the past is, they'll propose to interconnect, and again, they pick the location, they pick the area. We have no control of that. But they submit an application to interconnect. And what happened is, depending on how saturated the system is, then the next one that will interconnect will require major upgrades. So basically, we took all the juice out of the system already because we connected so many hundreds of megawatts of DER, especially in the Cape area. We connected already hundreds of megawatts safely, right? And I'll show later this type of studies we do, but that has been connected. And we were at a stage in the Cape where the next one in every substation will require significant upgrades, basically. And that was the beginning of what we call the SIP, right? The Capital Investment Project. So in the SIP, there's a construct where now we can study them. Instead of studying individual DER customers who basically, if you break it, you pay for it, right? That's basically the construct before. Within this SIP construct is, you have 10 of them in an area. Well, why don't we share the cost for the 10 of them? And at the same time, we build an infrastructure that is needed for electrification. So there's also an additional benefit to distribution customers. So, and we put and I have the docket there, but basically under this construct, you have a distribution customer benefit, a distribution reliability benefit that is benefiting the customers, and then there's the DER customer benefit. And the chart on the right shows how the breakdowns work basically for the entire SIP area in the Cape. So now for the customers for DER customers is beneficial because they get a fixed cost to interconnect to the system. They still have their own cost of the site cost, basically at their own location. But to connect to the system, instead of being the next one that breaks the camel's back and have to pay hundreds of millions of dollars, right? Now the cost is shared among the customers now and also the customers in the future. So that's what we call the SIP construct on the bottom. And basically, the cost is $357 per kilowatt for large DERs to interconnect into the distribution system. A little bit more detail about the group. So on the right side is the area that it covers. So again, there's certainty now. Any large DER, typically greater than 50 kW, has a fixed cost instead of before where, they have to find out at the end if they're the ones that basically, basically the ones that overload the system. So now there's a fixed cost. Anybody connecting will pay that cost to connect to the distribution system, plus their additional, we call it point of interconnection cost, basically at their site. If there's any additional cost, then they'll pay for that. But it's a fixed cost now, so it's a lot more certain. And the entire group, that green area covers about 8 substations, right? So anybody connecting to those substations, same thing. They pay the same fee. So we were able, with this construct that was already approved, to enable, in addition to the 149 megawatt that's already connected in the Cape, this group was able to enable 71 now, but then enable another 225 for the ones coming in. So not only are the ones connecting now help pay for it, but the ones connecting in the future help pay for it. And that's how we're able to reduce the cost to give customers certainty. Okay? And with that, I'll cover the next topic, which is more of a local DER installation. So there was questions about the Cape Country Club solar interconnection, and I'll just cover it a little briefly. But basically, we have 3 sites in the Cape Cod Country Club. We studied them. It's about 13.5 megawatts. Actually, a lot. It's a lot of generation. Actually, 13.5 is a good size. And there were questions about the impact on the grid, right? Just on the right side, I just put a little graphic of the process. But basically, when a customer submits an application, DER application, to interconnect to the system, we do what is called a system impact study. And we basically study everything that is needed to make sure that it doesn't affect the grid. So there's a lot of terms in there, but basically we do all kinds of analysis to make sure that the voltage and the current and nothing, there's no violations to the system, that nothing is going to happen. And we go through all those studies, and only when we identify that there's no violations, then the customer is approved. Sometimes upgrades are required. So let's say we study it, there's a violation, but if we upgrade these pieces here, then there's no violation. So as part of that, the customer has to pay for additional upgrades, basically at their own side. But once those upgrades are completed and they become part of that project, so before the customer connects, we do the upgrades, right? And that's how we're able to make sure the grid doesn't get affected in a negative way when we interconnect our customers. In a positive manner, well, we're producing, clean energy here in the Country Club, basically. There are some upgrades required for this project, actually. It was determined after the study. It is mostly distribution line upgrades. So the ones you see up on the poles, typically change them from a small size to a bigger size, and then that allows to have more currents, which reduces the trouble. So those are the type of upgrades that are required. I think about 4,000 feet of cable needs to be upgraded prior to that job. Now, what does not need to be done before that job is the work at the substation. So I think that the substation work can be done after, but this project can interconnect as long as those local distribution line upgrades are completed. Yep. Next one. And I pass it down to Jacob.
This is our last slide, and I'll cover this really quickly because I know we're going over on time, but we did get this question, and we just want to be fully responsive. So this final question is, are we considering new nuclear energy as an option, and how quickly can it be interconnected? Carissa touched on this earlier, but I'm just going to reemphasize here, right? So Eversource does not own, operate generation, large-scale generation. This was as a result of FERC Order 888, New England deregulated, and they had the utilities sell off all the generation in the late 1990s, so Eversource doesn't own large-scale generation, and Eversource also doesn't plan for future generation resource adequacy needs either. This is a function of ISO New England via their forward capacity market, but also states own resource adequacy, and so they'll do state procurements for generators. But with all that said, I did want to touch on, we are watching this very, very closely, as are many across industry. And there are 3 advanced nuclear reactor projects, small modular nuclear reactor projects I wanted to call your attention to. Many people across industry are watching these closely. The Darlington one up in Ontario, Canada, is the farthest along. It's going to be 1,200 megawatts in total, commencing construction with an in-service date only 5 years out. In 2030. A couple other projects here too as well. And just if you Google it, I mean, one of the things we really would like to see is the cost to come down, because the Darlington project, for example, I think is north of $15 billion for that project. So these SMRs that are coming online obviously require much less space, between 15 acres, which is much less. And just to put that in perspective, right, the Pilgrim plant that shut down was like 700 megawatts. And so the Darlington project's about 50% bigger than Pilgrim. So that's a pretty decent size there. Just to put that in perspective for you. So thanks. I think that wraps up our presentation. Looking forward to the questions.
Sure, I mean, if you want to take a look. So I guess I'm the keeper of the questions, me. I was remiss in not thanking you, Stephanie, and the Falmouth Energy Committee for having us here today. I didn't even thank you. So thank you so much for inviting us. Like I said, we love to come out and educate folks And I do want to give a shout out to Stephen Dudek, who's taking a picture actually right now in the back of the room, who organized all of this. It's really hard to herd the cats. We're a large company at Eversource, about 10,000 employees, and he did a fantastic job at helping to pull this presentation together with all of the subject matter experts. So I'm going to just try to maybe distribute these questions among all of you. I don't know I just got them now. So I think I'm going to just start with one that's probably a pretty quick answer. Is the current administration limiting funding / growth of energy development interconnection solutions? Example, wind and solar versus coal. So.
Forgot we needed a mic. You saw it on my slide. Every developer I speak to is very concerned about the future or the viability of their project because there is uncertainty. Are the tax credits going to be there? Will the state who issued an RFP actually negotiate and close that power purchase agreement? So nobody wants to develop until there's more certainty. So that is the impact by the federal government right now. It's made a little bit of a fickle situation.
Yeah, for the customers that are actually in queue now, we're trying to do as much as we can to make sure that the work is done, to make sure that they can get connected, to make sure they get the credit. So we're doing as much as we can to get them connected.
Yep. So I could take one while we sort through them. So, this is a hot topic. I'd be happy to follow up with anybody afterwards on this. But what is the long-term effect of AI computers on the power usage and expected increase in power needs? So I'll try to be quick. So this is something, even as recently as like 2 years ago, we had no interest in hyperscale data centers in New England. The cost of energy is just simply too high. That has changed. The tidal wave is here. At any given time, we'll have anywhere between 2,000 megawatts and 5,000 megawatts under study of hyperscale data centers. I will say, none of those have made them to construction or actual operation yet, but there's a lot of interest. And of course, so, and these projects can range anywhere in size of, 250 megawatts to upwards of 1,000 megawatts. And so when you talk about adding a single spot load that's equal to almost the entire electric load of New Hampshire, that has profound consequences to, I was talking earlier about resource adequacy. We're already a net importer. We're struggling to build large-scale generation. Solar DER is kind of one of the only things that we've got going. That's why we're trying to help bring on as much as we can. But at the same time, right, we are, as the transmission owner, distribution company, there are many laws that require us to provide open access to interconnection customers. So this isn't something that Eversource can reject or block. We have to just figure out how to make it work. And if they continue to advance through the development cycle, they will materialize. And so, but there is a lot of interest, and it is kind of here. It's kind of upon us. But the thing that's definitely keeping me up at night is the resource adequacy concern, which this question correctly highlights.
I think we're going to hand this to, I don't know if you handed it to Juan, but he handed it back to you.
Oh, nice. So why has New England load fallen from 2006 to the present? It's primarily through energy efficiency measures. There's been a lot of hard work from a lot of people, a lot of investment, et cetera, to deploy energy efficiency measures. Now the general school of thought is like kind of the easy low-hanging fruit has been kind of mostly picked already, and furthermore, right? So loads are starting to come back now. I mean, just as recently as like last year, I think we saw the largest single year-over-year load growth last year than we had in like a decade and a half. And that's great to see. And it's just through economic development. And so in many ways, that's great to see. Coming back to a 26,000 megawatt load last summer. Again, that's the highest load, as the graph showed, in many years. And so now it's just that the load growth, and especially when you start thinking, when you start taking into consideration electric vehicles, and in particular heat pumps for space heating, there's really no amount of energy efficiency that's going to be able to make up for that. Because, I mean, I should have said, right? So roughly, we're right now in New England is a 25,000 megawatt system. right? We did 26,000 megawatt peak last. So I'm just for the sake of math, 2050, that load is expected to be 50,000 megawatts. So the electric load of New England is expected to double in the next 25 years, resulting mostly from electric vehicle adoption and heat pumps. And then to Carissa's point, I think, or Juan, maybe it was JD, but also in 2035, that's why it's switching in around 2035 to a winter peaking system, just like our neighbors to the north are, because the heat pump load is tremendous. And it's going to, and gets very cold here, and so you combine all that, and there's no energy efficiency solution there. I mean, of course we should still do it, but we're talking about doubling the loads in New England over the next 25 years. It's staggering. But good question though. Thank you.
I can cover also a few. So on substation forecast, why is the demand dramatically increasing after 2030? Is it reducing gas availability? It's not based on the availability of generation. Basically what we do, and we have various components. So what we do is we look at the biggest driver of load most of the time is new business growth. So new buildings, right? That's the biggest driver. But also on the forecast components, we have many components. So you have the normal load growth. So basically somebody goes and buys a bigger TV, or somebody goes and enlarges their space at the house, but not to a significant amount where you require like a new service. That's your normal growth. That one we don't track, but we see it when we measure, right? And then you have the new businesses. Those are large. Those we measure, we track every year. We try to track them. And then we have EV as a component, electric vehicles as a component of the forecast. We have energy efficiency as a component of the forecast on the other side. So that's negative. That takes away from the demand, right? And then we take all those components and we just add them up, basically taking into account where we're going to see the most demand. And that's basically what drives this demand. It's nothing else than that, basically. It has nothing to do with generation. There's also another question. Do you capitalize future needs by increasing collection from ratepayers today?
So I think I think it's a rate question. So I think sort of historically utilities, we're not allowed to build it, or historically we haven't been allowed to build it and they will come, right? Say we're going to build this new line because we think there's going to be this load. Typically we do a study. We'll take that example of the line that was just built, Cape Cod Solution, the first phase, the Mid-Cape reliability. That was a study that was done. It took 10 years to kind of make it happen, between the study and then filing with the state and then constructing that project. We're almost behind the 8 ball, right? When we have to exhibit a need, and that project was an example of exhibiting a need. So I think the short answer is that we're not allowed to, with the caveat that the electric sector modernization plan kind of changes things, right? We submitted that plan to the state to meet Massachusetts climate goals, which they're not goals, actually, they're regulation at this point. I don't know if that'll change, but so that's a little bit different. We're meeting demand, but maybe Juan can anticipate a demand. Maybe Juan can talk a little bit about how we modulate that based on what we see in actual demand. Does that make sense?
Yes, and even for the electric sector modernization plan, right, even though it's actual law, what we've done on the electric sector modernization plan is we look at the 10-year, which is the things that we see, the customers that we see. And then when we propose a project, we're going to engineer it and build it in a way that I install what I need now, but then I have expansion capability for the future. So we're not building anything that we don't need in the next 10 years. We're building exactly what we need for the next 10 years. But, if I'm going to build a substation, get a bigger room and leave that box there empty. So in the future, when electrification comes in, I can fill that box, that space in the substation with something else. And that's the approach we're taking, to be cost effective. Yeah.
So you're not being charged for the empty spaces. We're all ratepayers, but honestly, we're all Eversource customers. I think. I know I am. So we're not charging we're not paying for that future that hasn't materialized yet.
Correct.
That room in the house that hasn't been filled.
Yeah, and the advantage is that it's a minimal cost. It's like the engineering cost and all that. When the expensive part is when you have to buy the equipment and install the equipment and do all the construction costs. That's the bigger cost, and that cost we're deferring it to when we actually need the equipment. Yeah. There's another question here. Are improvements on Cape Cod in Falmouth designed for more robust supply of export power? So I'm going to cover the distribution side, and then Johnny can cover the export power. But basically, at Falmouth Tap, we have dual needs, right? There's more than one need. So we're basically, again, we're co-optimizing. There's actually a distribution substation need because the substations around it need more capacity. So we're actually, at the distribution level, we're building a substation, to support the reliability of that area, and then the substations that will tie to that substation. So it's a reliability and a capacity need at the distribution level to supply customers. And then at the transmission level.
Yes, to add to what Juan said, right? The capacity and reliability need are in the Cape. It's not exporting. We talk about the some upgrades here related to the offshore wind interconnection and the power flow change over the history. But I just want to point out one specific example, the Cape Cod Solution Phase 1 that Carissa mentioned, that new 115 kilovolt transmission line that was planned and built. It was actually driven by reliability issue of the high load in the Cape, especially in summer. Summer Cape is popular vacation area, and the summer peak in Cape does not peak the same time as the rest of New England. It peaks in the weekend. So that line was to address actually the high load driven reliability issues in the Cape. But when Carissa mentioned the co-optimization piece, was that we also found out later to interconnect the later offshore wind, this line can also contribute to the renewable integration if it runs at a higher voltage level. So we planned that new line, the project, for improving reliability on the Cape, and also co-optimize with the renewable integration.
Add really quickly on that. So just to add one more thing on that project in particular. So the Mid-Cape Reliability Project that Jenny just referenced, that was phase 1. Also, the actual materials used, and in particular the conductors, so the wires essentially that are suspended by the structures, is really a grid enhancing technology. It's an advanced high temperature, low sag conductor. It's very highly specialized, and it provides about twice the capacity of many of our other lines. And so this is and in addition to that, we're doing we got federal funding from the Department of Energy to do a dynamic line rating project on the 345 kV line coming out of the Cape, just to further help optimize and hone the ratings on these facilities. So I just want to bring up those two projects in particular and mention that we're using advanced conductors. It's often something that we don't have an opportunity to talk about, so thank you for asking the question. And so here's a question. So if offshore wind is changing Cape Cod from a net importer to a net exporter of electricity, how does that change or how does that impact the reliability and cost of electricity in Falmouth? So what I'll say is, and a lot of the content of the presentation we just had, it was dense, and so we weren't able to kind of touch on all the details. So I'll just take this question to just emphasize that part of the interconnection process that Carissa was talking about, the entire purpose of the studies is to ensure that when a large generator is interconnecting, that they essentially cause no adverse impact to the reliability of the grid and the existing customers. And so Vineyard Wind, for example, it's interconnecting at Eversource's Barnstable substation, right? It was identified that, without going too much into the weeds, but there were some voltage issues, and so Vineyard Wind had to install very large, they're called synchronous condensers, but essentially they allow them to, they're large rotating machines that essentially allow them to regulate voltage at their point of interconnection. That was required, that requirement was imposed on them to essentially ensure the reliability wasn't degraded. And that's one of the things that we do in the study process when we're studying these large generators. And then the other point I'll kind of say in terms of reliability, right? I mean, as a general matter, being located closer to large generators theoretically could reduce the number of system contingencies where you could be impacted from a reliability perspective during a storm, et cetera. And so, it doesn't really, so I don't want to say it's helpful. 'Cause I'm neutral. I'm a neutral party here, but there are some advantages to being located nearby to large generation. And then just on the cost, I'll just say this, right? So, Eversource, the largest portion of residential electric bills is generation supply. And Eversource, it's simply a pass-through. Eversource makes no money on the cost of energy. And so I'll leave it at that. Thanks. Any other questions? Or?
I'm sorry. We're deciphering one of the other questions, so we might have a question back to you. Okay, I wanted to build on the comments that Janie was making and Jacob was making as I answer this question. Given all the costs get passed to ratepayers, what more can utilities like Eversource do to remove the cost of interconnecting offshore wind on Cape Cod and throughout Massachusetts? So this is a great question, and I'm going to direct you back to my slide deck. You heard about Cape Cod Solution, the Phase 1 project. We built it and it's operating today at 115 kV, but it was built out so it could operate at 345 kV. All right, really smart move, co-optimization. One of the things that I do on the interconnection side, every interconnection that comes across my desk, doesn't matter if it's a generator or a load project like a data center, I look to see, do we have an asset condition project? Do we have a reliability project in the area? Is there an opportunity to co-optimize? I think you're going to find at Eversource, we do that with every single project these days because we're trying to find the low cost, most effective solution to bring on that project, that generator, that renewable. So hopefully I answered that question. This next question is along the same lines. Why is Massachusetts energy use going down, and what are the estimated costs of clean energy grid by 2050? I apologize, I don't have a crystal ball, but in my slide deck, I did mention there are so many things changing at the state and the federal level. I don't think anyone could predict at this point in time what future energy rates would be in 2050. I think we just have to continue to pay attention to policy and what our states and our regulators do. And then along that same line, I have this third question. In the 2050 heavy wind solar plan, how much of the intermittent supply is expected to be covered by load control versus grid battery storage versus backup fossil fuel generation? Great question. I look at the usage every single day because I'm trying to figure out the answer to this question too. But in my slide deck, I think I pointed out having a battery storage facility that can capture that excess wind, especially in the evening, say 11, 12, 2 o'clock in the morning, it can be stored in a battery storage facility that can then be turned around and used during the peak hours, say 1, 2, 3 o'clock in the afternoon. So that's one way that it can all work together. But I have to agree with Jacob. I think we're starting to see energy efficiency measures kind of ramping back up again. 10 years ago or so, they were at a peak, then they diminished a little bit, but look at it. Everybody has LEDs in their houses today, right? You have switches to turn things off turn things off automatically when you leave the room, or you've gotten to be conscious again like you did in the 70s to turn off those light switches. So I think there's more energy efficiency coming. Those were my three. Oh, go ahead.
Were you gonna? Did you have more? Because I want to add something on this. This is really a good question because there's a flip side to adding all these renewables, and one of them is, and I would encourage you. So one of the things that we always monitor every single year, New England sets a new record of minimum load, and why that's happening is because we're installing a lot of solar. It's called the duck curve, if you ever want to Google this. ISO 91 has put out some charts on it. But essentially, in the middle of the day, in springtime usually, because that exacerbates this reliability concern, because in springtime electric loads are generally lower. But all the solar is essentially peaking at the same time, and it pulls down the total load right in the middle of the day. Now, this causes several concerns, not the least of which is we're right about at the border, the minimum run output of the combined nuclear fleet. Nuclear plants don't like to move their dispatch around a lot, so that's one thing that's happening. But also, right, we're struggling building interregional transmission, and the worst case scenario is we build all these clean energy resources, and then we can't use them because we can't move the power to our neighbors, et cetera, and we don't have loads high enough in the middle of the day, and we have to spill the solar or spill the wind. And this is one of the value propositions of storage. But storage right now, lithium-ion batteries are not very energy dense, and so we're looking at 10-year out planning cases where all of New England's load is 300 megawatts. 300 megawatts. That's about the size of Cape Cod, right today. And so it's truly incredible, but it's one of these, like, people have to ask, like, hey, what are the kind of consequences and maybe unintended consequences you kind of have to plan for large renewable penetration? This is one of them, and we're seeing it play out. So every single year, and ISO 91 always sends out a press alert whenever it happens. I can't remember where they were this last summer. I think it was about 5,500 megawatts or so. But I just wanted to mention that because then obviously the other thing is on that same day, when loads are so low in the middle of the day, now you have this massive ramp up of electric load as the sun starts setting. And so now you need flexible generation to be able to ramp that fast, because a lot of large generators take a lot of time, 6 to 8 hours in many cases, to be able to ramp up their generation output. So now you have this very steep climb up of electric load because the sun's setting. And so this is where the value proposition of storage enters, because you capture it in midday, you can potentially deploy it in the storage, and so that's where we are seeing. That's public, right? The 150 megawatt battery storage that was.
In Massachusetts, there was 2 projects that went commercial in the second half of 2025. One in the Carver area of Massachusetts, and the other one in the Plymouth area. So we're upwards about 400 megawatts just over the bridges of battery storage. Oh, wait.
Yeah, we still have one. So, which ties back actually to that reference that Jacob made, is what happens in worst case. I think it says Monday with snow, but just from the overall perspective, our worst case right now, it's still the summer, because of, turning on the ACs. We are starting to do analysis on the worst case on the shoulder months. We call shoulder months when the load is very light, but there is a lot of generation, renewables, any type of generation. So at that point, now we can see another worst case, which is the system going backwards. So what is the worst case on the system going backwards? Meaning you have the generation at the distribution level is going back to the transmission. So we have to make sure every component, we know how to plan this way, all the way from the transmission back to the generation. We also know how to plan the other way, but now it's changing, right? And now it's going, when it goes backwards, it's actually exceeding now limits that we have to plan for. So, we have a lot of very smart folks who studying that, and, we'll obviously find a solution for that case that Jacob said, but, that is the worst case scenario. Your shoulder months and basically your summer. Still summer. 10 years from now, maybe it's not. Maybe it is your shoulder months. And maybe, 15, 20 years from now, it's not. Maybe it's the winter when, everybody electrifies to heating, and then we have not enough generation. So it changes, but right now we're still in the summer. There's another question on where will the transformers come from? I'm assuming it talks about substation transformers, and we have an entire process for that. Typically, there's big manufacturers that do this, typically out of seas, but there's also within the United States. But that's more of a complex process because it goes into, which one is the developer that has the most benefit costs and all that. But it comes from all over the world. There's only a handful of, manufacturing facilities that can do this type of equipment. So there's a handful, and it covers the entire world, basically. And then average age of distribution. So the distribution system, it can go all the way from like just installed to, 40, 50, 60 years. So it depends. It varies basically by area. We are constantly upgrading it because, these are mechanical equipments, right? They get old, they rust. So we're constantly upgrading. The age varies depending on the area. And then the last question, which was what we were asking us, is cables from wind farms, where do they connect to? And there's a reference to Somerset. I know they're connecting to Barnstable, right? Is that?
There's Barnstable. Yeah, that's generally the area has been West Barnstable. So I'm not sure why someone brought up Somerset. But if you want to follow up with us afterwards, we're happy to kind of drill down on that one.
I think what we'll do is that thank the group of experts for coming today for an excellent presentation.